For those of you who are attending class via Zoom, please type something into the chat to let me know that you are present. And marginally paying attention. For the rest of you, the roll sheet is being circulated. All right. All right, today we are going to be talking about negative feedback amplifiers. And we are going to start by realizing them with the practical op-amp model and then move towards the conditions of ideality, which will allow us to apply the ideal op-amp model. And we'll see what comes of that. So, just a moment to get my cables organized in a way that my laptop is charging. There we go. All right, so let's start with the following negative feedback amplifier. Oh, and it would probably help if you guys could see the screen. All right. And minimize this. Let me make sure what's going on. Just people saying chat. Okay, great. All right. So a negative feedback amplifier is one in which there's a feedback path between the inverting input and the output terminal. So let's consider this guy. Where I'm going to have a resistor R2 placed in the feedback position between my output terminal and my inverting input terminal. I am also going to have a resistor R1, which I am going to apply between my inverting input terminal and my actual input signal, which I'm going to call Vin. And I am going to ground my non-inverting input terminal, like so. So this is going to be a numerical problem, so I need to define a few parameters. So let's first say that our resistor R1 has a value of 5 kiloohms. Let's say resistor R2 has a value of 10 kiloohms. The input resistance of the op-amp is 1 megaohm. The output resistance of the op-amp is 100 ohms. And the open loop voltage gain, AVOL, of the op-amp is 10 to the 5 volts per volt. So that would be 100,000. And our input signal, Vin, will be a simple DC voltage having a value of 1 volt. And I'm choosing to use that DC voltage of 1 volt because we're going to be trying to determine several of this particular amplifier's properties. So I'll go ahead and list those out. Our first thing that we are going to try to determine since we have an amplifier, we usually want to know what the output voltage Vout is. Our second quantity of interest is what I'm going to call the closed loop voltage gain, AVCL. Okay, so we should observe that by applying negative feedback, our closed loop voltage gain should be significantly smaller than our open loop voltage gain of approximately 100,000. We are going to try to find the input resistance as seen by our input voltage source. So we're going to be applying Thevenin's theorem. We are going to try to find our output resistance as seen from the looking into the output terminal. Also going to require the use of Thevenin's theorem. And then lastly, we are going to try to determine our differential voltage. And honestly, we're probably going to figure out E before we get C and D. I wrote them down in that weird order for whatever reason. All right, so we are given practical op-amp parameters. So we're going to work this using the practical op-amp model. One of the hardest parts of this problem is literally going to be just redrawing this thing to make sure that we're doing it correctly. So I'm going to take a moment to do just that. So I'm going to apply my input signal. This will be my inverting input here. Here's my input resistance of 1 mega ohm. Here is my non-inverting input. And so my differential voltage VD is going to be defined with a positive polarity on bottom. I'm drawing this stage right here upside down purely to make the feedback loop easier to draw because the feedback is connected from the negative or the inverting terminal to the output. So this is different than I've drawn it in previous diagrams, purely to make the overall picture look nicer. As long as my differential voltage is V plus minus V minus, I'm good to go. I can draw it V plus on top or V minus on top, however I feel like doing it. So I just wanted to be clear about that. Over here on the right-hand side of my model, I have AVOL. Actually, let me put in the numerical value. 10 to the 5 times my differential voltage VD. Here is my output resistance of 100 ohms, and I am measuring my output voltage between these terminals. So everything I've done up to this point is just the practical op-amp model where I've swapped the polarity on my input resistance. Now I need to go through and actually connect things. So for instance, between my non-inverting input terminal and ground, right here, I have a short circuit. So I'm going to short that to ground. Between my inverting input terminal and ground, I see that resistor R1 in series with my voltage source Vn. And then the only thing I have left to worry about is my feedback loop. Oh, sorry, that resistor R1 has a value of 5 kilo ohms. Might as well draw it. And now I have my feedback loop, which is connecting from my inverting input terminal to my output terminal. So across here. And this guy has a value of 10 kilo ohms. So before we move along here and start worrying about our circuit analysis and stuff like that, does everybody understand why what I've drawn on the bottom is a correct representation of the op-amp circuit up top? Everybody's on board with this. All right, so I'm going to use nodal analysis at the inverting input terminal and the output terminal to determine most of my quantities here, okay? So okay. So let's see, KCL at inverting input. And just as a quick aside, I'm going to replace Vn with its actual value of 1 volt. So my currents leaving my inverting input terminal are this guy to the left, this guy up and to the right, and then this guy to the right. So that's going to look like V minus 1 volt divided by 5 kilo ohms plus V minus 0 divided by 1 mega ohm. That's my current directed to the right. Plus, oh goodness, what did I just do? Forgot to label my output voltage. V minus, sorry, just a second, save, close, discard. Stupid error. Alrighty, sorry about that. So I'm going to have V minus V out divided by 10 kilo ohms and set this equal to 0. And now I'm going to do Kirchhoff's current law at my output terminal. So to be clear, I'm going to be adding this current and this current together. There's no current flowing through the open circuit, so it should just have the 2 terms. And so that's going to look like V out. My dumb finger would stop accidentally pressing that thing. V out. So minus 10 to the 5 VD. But what's VD going to be in this case? I disagree. So VD is always the voltage present at the non-inverting input terminal minus the voltage present at the inverting input terminal. So what voltage is at the non-inverting input terminal? 0. It's ground, right? This guy is connected directly to ground. This guy is labeled as V minus. So VD is 0 minus V minus is negative V minus. So I'm going to have V out plus 10 to the 5 V minus is my V out minus AV VD. So to be clear, I'm trying to figure out what this current is right here. So I've got this node, which is V out, minus this node, which is 10 to the 5 times negative V minus, which is where I get plus V minus. This is divided by 100 ohms. Is that clear? Just doing good old Ohm's law, finding the current flowing to the left through the 100 ohm resistor. So the voltage drop is the voltage on the right node minus the voltage present at the left node divided by the resistor value. All right, and then to that, I'm going to add V out minus V minus divided by 10 kiloohms and set these guys equal to 0. And so I now have two equations with two unknowns, V minus and V out, and so I can solve for both of them. So when I solved for both, I found that V minus is equal to 20.199 microvolts, and my output voltage V out was equal to negative 1.9999392 volts. So we actually already have enough information to solve for 3 of these 5 things I'm asking about. All right. The first one, V out is equal to what? We did that directly, right? We know that our output voltage is negative 1.9999392 volts. So something very, very close to negative 2 volts. All right. So part A is taken care of. Let's do part E while we're at it. We talked a moment ago and said that VD is the voltage present at the non-inverting input terminal, which is 0, minus the voltage present at the inverting input terminal, which is 20.199 microvolt. So obviously then VD is just negative 20.199 microvolts. So let me squeak that in right here. Our voltage gain is going to be defined, our closed loop voltage gain specifically, AVCL is simply the ratio of the output voltage divided by the input voltage that generates that output voltage. So in this case, this is why I chose a Vin value of 1 volt. It is just V out without a unit. So negative 1.9999392. Or you might see it as having units of volts per volt because it is voltage gain. All right, so that is 3 of the 5 quantities. We have solved part A, part B, and part E. Our input resistance, we're about to talk about, it's going to be fairly trivial. Our output resistance is going to be less so, all right? So I'm going to erase these arrows. Quick. Very, very brief review of Ohm's law. If I have a black box under test, I'm going to write this as DUT for device under test. And I want to determine its resistance. How can I do it? If I apply some known voltage, Vx, across the device and measure the current flowing through it, its resistance is simply the ratio of Vx over Ix, okay? So I would argue, if I'm trying to find the input resistance of my op amp, and I have already applied a test voltage of 1 volt, This is my current Ix that I'm trying to find in order to get my input resistance. Does that make sense? All right. So that begs the question, how am I going to determine that input resistance? Excuse me, that input current Ix.
Wouldn't that be our first? Is that our ACL at the output?
Putting too much effort into it. Okay. So let me ask you a question. Do I know the voltage at this node that I've circled?
Yes.
It's a 1 volt, right? Do I know the voltage at this node? So why not just use Ohm's law, right? 1 volt minus V minus divided by 5 kilo ohms will give us our current Ix. So 1 volt minus 20.199 microvolts divided by 5 kilo ohms gives me a number I didn't write down, but let me save myself here for something that I did write down. If I divide that as the denominator, here's how I figure out Rn. So I have my 1 volt applied, I divide by the current that's leaving the 1 volt source, and I get 5,000.100,997 ohms. So we can make an observation here for this amplifier in which we have placed the input signal on the inverting terminal. Our input resistance is going to be really, really close to this R1 value every time. Okay. If we had placed the input signal here and grounded that terminal, our input resistance is going to be really, really close to the internal input resistance of the op amp. Okay, so just a general rule of thumb. So for when the input is applied at the inverting terminal, it's close to R1. When the input is applied at the non-inverting terminal, it's close to the actual op amp resistance. All right, for our output resistance, this is where things are going to get a little bit more difficult, okay? How many of you guys remember Thevenin's theorem? So Thevenin's theorem says that I can find the equivalent resistance of any 2-port linear network if I can find the open circuit voltage and the short circuit current, and then the ratio of those two is the resistance. So here is our 2-port network. We're looking at this guy from our output terminals. Do we know the open circuit voltage? Yes, that's the V out we just calculated. So now what we have to do is short circuit these terminals and figure out what that current that's flowing through those terminals is, and that will allow us to calculate our output resistance. So let me just draw a quick short circuit here, and I'm going to call this guy I Norton. And so what does that change with regards to these equations? So let's look at this first equation here, right? Okay. V out is now defined to be the voltage drop over that short circuit. So what does V out have to be? 0 volts. So that means we have one equation, one unknown, in which we can find our voltage V minus. And then we can do Kirchhoff's current law at our output node, saying this current in plus this current in is equal to I Norton, and we're good to go. Does that make sense? So jumping ahead just a little bit, the methodology is there. I don't feel I need to waste 5 minutes actually rewriting those almost exact same equations. We find that our Norton current, I Norton, is equal to negative 664.45176 amperes, which gives us an output resistance, R out, of negative 1.9999392 volts divided by negative 664.45176 amps. What the heck is happening? Is equal to 3.0085 milliohms, or thousandths of an ohm. Okay. So what is effectively happening here is, and this is going to be true for any negative feedback op-amp circuit, or it doesn't matter where our input is applied, because we're speaking strictly about the output resistance. If our resistive network that we have applied, in this case the 5 kilo ohm resistor and the 10 kilo ohm resistor, is significantly larger than the internal output resistance of the op-amp, then it looks like a short circuit. It's going to look very, very close to having no output resistance, which is why we see 3 milliohms, extraordinarily tiny. Okay, so any negative feedback amplifier, we should expect to see our output resistance pretty dang close to looking like a short circuit. Okay. All right, so this was a pretty fair amount of math. It would be great if we didn't have to do so dang much, right? If you had to analyze every negative feedback circuit like this, it would take forever. So let's go back a bit and talk about what it means to be an ideal amplifier, okay? And these next 5 minutes or whatever should largely be a review of that video that you watched when I was out sick. So for a generic amplifier circuit where we have some voltage Vs of t connected to some source resistance Rs, so we're realizing a practical voltage source at our input terminals. Here is our input resistance. Here is AV times Vn of t, where Vn of t is the voltage drop over our input resistance. Or out. Here is V out, and then we may have a load resistance RL connected to our output, like so, such that there is some load voltage VL as a function of T. All right, and just to make everything ludicrously clear, On the left-hand side, we have our source or input. On the right-hand side, we have our load section where we take our output. And in the middle, we have our generic amplifier circuit, okay? In an ideal case, we would see that our output signal, VL of t, is just a scaled version of our input signal, Vs of t. So ideally, VL of t is some voltage gain AV multiplied by our source voltage Vs of t. So my question to you guys is, what value of Rn makes Vn of t exactly equal to Vs of t? Zero? So if we applied a short circuit here, Vn of t would be exactly equal to 0 volts because the voltage drop over a short circuit is always 0. So we actually need something on the completely other side of the spectrum, right? If we were to apply an open circuit here or an infinite resistance, Vs of t would have to be equal to Vn of t because there would be no voltage drop over that resistor Rs. So ideally, Rn is infinitely large. Now, under that condition, we have Vn is equal to Vs. It's amplified by this voltage AV. So here we have AV times Vs. What value of R out makes V out equal to AV times Vs? Zero, right. So if we put a short circuit here, all of this voltage at our amplifier stage gets transferred to the output. So R out is equal to 0, and it's impossible to see it here, but ideally our voltage gain of our amplifier, the open loop voltage gain specifically, would be infinitely large. So I want us to rework that problem that we just did using these parameters instead, and we're going to find out something pretty great, pretty quick too. So if I redraw my circuit, let's see. So this is infinity ohms, so we're treating it like an open circuit. This is V plus, this is V minus. Over here, I have infinity times VD, where my differential voltage here is VD. I have 0 ohms here, so we're treating this guy like a short circuit. Here's my output voltage, V out. Let me put my ground right here. All right, so my non-inverting input terminal is connected to ground. My inverting input terminal is connected to one leg of that 5 kilo ohm resistor. which was in turn connected to the positive polarity terminal of my 1 volt source. I also have my feedback resistor here. And kilo ohms. All right. So if I apply Kirchhoff's voltage law at my inverting input, I get V minus 1 volt over 5 kilo ohms plus V minus V out over 10 kilo ohms is equal to 0. So this leads me to an important observation. I'm throwing away the term of current flowing through my input resistance of my op amp because I'm treating it as an open circuit. So this is where ideal op amp rule number 1 comes from. There can be no current flowing into or out of the input terminals of an ideal op amp is because we are saying that it has an infinite input impedance, right? So I'm going to write that guy right here. Out of the input terminals of an ideal. All right. Now I'm going to do Kirchhoff's voltage law at my output, okay? So not Kirchhoff's current law, Kirchhoff's voltage law. I get infinity times my differential voltage VD is equal to my output voltage VL, right? If I do KVL, and I know that I have a short circuit here, so there is no voltage drop, V out is exactly equal to infinity times VD. Nothing particularly difficult about that, but it may seem like this equation doesn't help us. So I'm going to use algebra and rearrange it really slightly. VD is now equal to V out over infinity, which means what? My differential voltage VD is 0, which means the voltage present at my inverting input terminal must be identical to the voltage present at my non-inverting input terminal. So this guy tells me that V plus minus V minus is equal to 0. This is what's known as our voltage constraint, and it is where ideal op amp rule number 2 comes from. There is no voltage difference. Dang it, I have to save this, close it, and then reopen it. Again, I apologize. It's my thumb pressing a weird button on this new stylus I have. There is no voltage difference between the input terminals of an ideal op amp. All right. And so those two rules now provide us with enough information to be able to solve for V out for our given input voltage of 1 volt, right? Because if we know that V minus is exactly equal to V plus is 0 volts, then this becomes, we do it in blue. So we have -1 over 5, or -1 volt over 5 kilo ohms is equal to negative V out, or sorry, plus negative V out over 10 kilo ohms is equal to 0, gives us V out is equal to -2 volts. So we get almost exactly the same answer as we had before, but with significantly less effort. All right. So for any negative feedback op amp circuit, and only negative feedback op amp circuits, unless you are told otherwise, treat it as if it were an ideal op amp circuit, because we can see that using practical values gave us answers extraordinarily close to what we would have gotten just using the ideal values. The difference between them is what is called the gain error of the system. And if your open loop gain of your op amp is very, very large, your gain error is very, very small. So for negative feedback op amp circuits and negative feedback op amp circuits only, from here on out, unless you are told otherwise, treat them as if they were ideal op amps. So with that in mind, let us now go over the, however, I think it's like 4 basic rules of solving literally any ideal op amp circuit. And then we can work a couple of examples or knock off early, because at this point, it's literally review of circuits 1 crap. So solving ideal op amp circuits. Step 1. Apply rule number 1. There is no current flowing into or out of the input. Step 2 is apply rule number 2. V plus is equal to V minus, just using a shorthand notation here. Step 3, determine V plus, the voltage present at the non-inverting input terminal. Step 4, use V plus to find V out. That's it. 4 steps. You follow these 4 steps, you will be able to solve any negative feedback op amp circuit. So I'm going to draw a gnarly-ish looking one that I might be representative of something hard that you would have seen on a circuits 1 test. I'm going to amend rule 4 slightly. Instead of just arbitrarily saying use V plus to find V out, I'm going to say use V plus to find V out by applying KCL at our inverting input terminal. I'm being more specific, telling you exactly how to use V plus in order to get the result. Okay. So this is a horrifyingly ugly circuit, and we're going to solve it in 2 minutes or so. So if I apply op-amp rule number 1, that means that this current is 0 amps, and this current is 0 amps. When I apply op-amp rule number 2, that means that this voltage right here, V plus, is the same as this voltage right here, V minus. So we've already knocked out the first 2 steps. How do I determine step 3, what my voltage present at my non-inverting input terminal is? Voltage division, perfectly reasonable, because we know that no current can branch off and flow through. So based on the ratio of these resistances, what are we going to have? 3 times 5/6, right? So 15 over 6. Easy enough. Now we apply KCL at this node, recognizing that V plus is exactly equal to V minus. So that is going to give us, let's be explicit here. I'm going to be summing this current plus this current plus this current. So that is going to give me 15/6 of a volt minus 1 volt over 4 kiloohms minus 2 milliamps plus 15/6 of a volt minus V out divided by 10 kiloohms equal to 0. 1 equation, 1 unknown. My calculator can solve that trivially. We're done. That's as hard as this can get. And it takes that level of effort if you apply those 4 steps. So, do we need to beat this dead horse further? All right. So we're knocking off, it looks like, what, 20, 25 minutes early today. I got no problem with that. It's a Friday. On Monday, because today is Friday, yeah. On Monday, we are going to cover common operational amplifier topologies, which means we're going to define inverting op amps, non-inverting op amps, voltage summers, differencing op amps, differentiating op amps, and integrating op amps. Largely a review of what we did in circuits 1. I might talk about gain error and a couple of little things like that just to make it slightly less boring than of that lecture from circuits 1. Maybe not. We'll see how I feel. On Wednesday is going to be our last lecture on the op amp section. So over the weekend, I am going to put up a selection of design problems for you guys to look at. I want you, there's roughly 20-ish students in here. So I think groups of 3 would be appropriate. I believe I'm going to give you 4 options to choose from. And so your group of 3 will just complete 2 of those 4 options. I'll put the specifics and all that kind of stuff online. But we're close enough to the end of op amps to where I feel comfortable giving you some design problems to work on some things. So it's going to be practical op amp type stuff. And what I mean by that is I'm going to ask you to, so one of your options might be to develop a better 1-bit analog to digital converter. So we did one that was really crappy with a comparator. You're going to, one option is to do one with a spit trigger. Another option might be to set up a circuit to be used at a way station or something like that. So if you have a 4-axis vehicle that drives across load cells, to be able to sum all of those input signals together and convert that output signal to the specific weight of the vehicle using resistor ratios. Another thing might be a controls problem where you have a sensor that outputs a specific current range in milliamps, and you need to convert that to a specific voltage range that can be read by your PLC. Another thing might be more analog signal processing. So if you have an input square wave, excuse me, an input sinusoidal wave of 1 volt peak to peak, develop a circuit to give me an output that is a 1 volt peak to peak square wave and a second output that is a 1 volt peak to peak triangular wave, something like that. So you're going to be applying all of the different circuitries and all that kind of stuff, positive feedback all the way through negative feedback through cascading amplifiers together to be able to complete all of these design problems. So I feel like it's a good way to sum things up and get you ready for moving along. All right, that's enough jibber jabber out of me for today. So I'll see you guys on Monday.